Last class, we have discussed about some of the basic concepts of DC machine, and in this class, we are going to discuss about few more concepts of a DC machine, namely statically induced EMF and dynamically induced EMF, and analogy between electric and magnetic circuits. You are expected to refer Principles of Electric Machines and Power Electronics by Dr. P.C. Sen. Earlier, we have discussed Faraday's law of electromagnetic induction. Whenever a conductor cuts lines of magnetic flux, an EMF is induced in the conductor. It's his first law. And in the second law says that induced EMF E is equal to minus N d phi by dt. Here we discuss about the magnitude of induced EMF. Refer figure 1a, conductor with length L moving at a velocity v right angle to constant flux density. The conductor shown here and the full length of the conductor is inside the magnetic field and length of the conductor is L here. And the flux density direction is this way, north to south pole, indicated in the figure. And the conductor is rotating at a velocity v which is right angle to the flux density, meaning orthogonal, that is the angle between these two becomes 90 degree. These two becomes 90 degree. Flux cutting by the conductor d phi is equal to Va. We know from the previous discussion, flux density B is equal to phi by A. From this, we can write phi is equal to B into A, where area swept by the conductor A is equal to L dx. Hence, d phi is equal to BL dx. Using Faraday's law, E is equal to d phi by dt, and making use of d phi value here, I can write BL dx by dt, which is equal to BLV. Consider figure 1b. Conductor is moving with a velocity v, making an angle theta here with the direction of magnetic field. Effective velocity at right angle to the magnetic field V effective is equal to V sin theta. Induced EMF is equal to E BLV sin theta. When the conductor is moving along the direction of the magnetic field, meaning magnetic field is this direction and conductor also moving in this direction. So this is B and this is the conductor, current carrying conductor. I refer to C. And theta becomes naturally 0. So sin 0, 0. Hence induced EMF E is equal to 0. An EMF is said to be induced when the flux linking with the conductor or coil changes. This induced EMF can be classified into two types: statically induced EMF, which is applicable to transformer, and dynamically induced EMF, which is applicable to generator. In statically induced EMF, we further classify into self-induced EMF and mutually induced EMF. In statically induced EMF, we keep the coil and the magnetic field system, both are stationary. The change in flux linking the coil takes place neither moving the conductor nor the field system. Both are kept at stationary. Example, EMF induced in a transformer. It has got no moving parts. In dynamically induced EMF, the magnetic field system is kept stationary and the conductor is moving, or the field system is moving and the conductor is stationary. So thus by following either of the two processes, the conductor cuts across the magnetic field and the EMF is induced in the coil. Either the field system is moving or the conductor is moving. Example of devices which induces EMF in such a way called as generators and back EMF of a motor, which is depicted in this diagram. The basic principles of magnetic fields are: a current carrying wire produces a magnetic field in the area around it, and generator action refers a moving wire in the presence of a magnetic field has a voltage induced in it. And the third one, motor action, a current carrying wire in the presence of a magnetic field has a force induced on it. And fourth one, transformer action, a time changing magnetic field. Time changing magnetic field, alternating magnetic field, induces a voltage in a coil of wire if it passes through that coil. Any DC machine can act either as a generator or a motor, depending upon the type of input applied at the input terminal of the machine. Here we discuss about the analogy between electric circuit and magnetic circuit. Electromotive force involved in an electric circuit is analogous to magnetomotive force in ampere turns in a magnetic circuit. Similarly, current in ampere analogous to magnetic flux in Weber. Conductivity in mho is analogous to permeability in Henry per meter. Resistance in ohm in electric circuits and reluctance in ampere turns per Weber in magnetic circuit. Electric field strength in volt per meter in electric circuit. Magnetic field strength in ampere per meter. Current density J in ampere per meter square in electric circuit. And in magnetic circuit, magnetic flux density B in Weber per meter square or Tesla. In electric circuit, Kirchhoff's current and voltage law is applicable to electric circuits. And in magnetic circuit, Kirchhoff's flux and MMF law is applicable. The diagram shows the analogy between electric circuit and magnetic circuit. Look at in an electric circuit, driving force is EMF E produces the current I, which is limited by the resistance R. And in a magnetic circuit, driving force is magnetomotive force, produces the flux phi, which is limited by the reluctance shown here. So far, we have discussed how the force in a conductor and EMF induced in a conductor is determined. Also, we discussed the statically induced EMF and dynamically induced EMF, and we have compared the analogy between electric circuit and magnetic circuit. In the next class, we will be discussing about the constructional features of a DC machine. Thank you.